Hi, hello everyone. I'm Vivian, and it's my great honor to be here today. And I'm the maintainer of the CNCF Wasm project.
Hello, everyone. My name is Michael Yuan. I work at the Second State and also the founder and maintainer of the Wasm project. So we want to talk about, a new use case. We have seen a lot of traction since Wasm last year. So we came here last I/O. I gave a talk about, at the time ChatGPT just came out. We talked about running ChatGPT extensions within Wasm and things like that. We've seen a lot of use cases with Wasm in the large language model throughout this year. So we want to talk about that. Please.
So today, Michael and I will talk about how to create cognitive agents and extensions for LLMs using WebAssembly. LLMs has been very popular and a powerful tool for our daily life and work. So as a new kind of workload, LLM apps raise some new demands in the cognitive tech stack. So we will talk about the current tech stack for LLM apps and its limitations, and then we will talk about how WebAssembly can solve the problems. During this talk, we will have 2 demos if we have enough time. Okay, let's start. So the first is the current tech stack for LLMs is dominated by Python. We use Python to do LLM inference. We use LangChain and Python to develop LLM agent or LLM extensions. However, Python also has its problems. The first one is that Python is heavyweight because it has lots of dependencies. It also makes it difficult for developers to install. On the left image, Chris Alban, he is the engineer director of Wikipedia, and he has entered the problem that he has entered some problems when he wants to install Python on his new MacBook. And the right image is Greg Brockman. He is the CTO of OpenAI, and he also believes that dealing with Python dependencies is the most important work in machine learning engineering. So from the view of LLM agents, Python is too heavyweight and with lots of complex dependencies. So for the LLM inference, the big problem is that the AI apps is not portable. We have lots kinds of GPU device, so we need to repair our app again to match the new hardware. Because the AI app is not importable, so as a result, we are forced to use API server. But however, API server is not flexible and performant. For example, if we want to develop an LLM app with multiple models, the OpenAI API server is not sufficient. So there is a need that we need to write LLM inference directly. And moreover, even Python itself is not cross-device portable. So in summary, the current tech stack for LLM apps is not portable and it's heavyweight. So we think Wasm can solve those problems.
Okay. Well, so how does Wasm solve this problem? I heard a lot of talk today that talked about the history of computing from assembly language to Java. So one of the old issues we thought we have solved 20 years ago, 30 years ago with Java has now come back. It's how do we write once, run anywhere? Java solved this problem, when you compile with CPUs, right? But today, if you look at, there's Macintosh has its own GPU, NVIDIA has its own GPU, AMD has its own GPU. Every single cloud provider now have their own GPUs, right? So it's no longer the case that I can write application on my laptop, compile, and expect to run on the cloud server. I will have to recompile it for the cloud server every single time again. When I use tools like container tools and Kubernetes, I can no longer rely on them to distribute my binary artifacts, because if I have a binary that is compiled for the Mac and I accidentally deploy it on an NVIDIA device, it would not run there. So portability has really come back with a vengeance. Is that how do we solve the portability problem all over again, but not for CPUs this time, but for GPUs? That's that actually is one of the most interesting challenges. We see how people use Wasm to address those issues. So in a way, I don't know why it's in a way that Wasm solved this. We're going to talk about in a minute how Wasm solved this problem. But the second, I think, equally important, is that Wasm, when you use Wasm to write GPU applications or AI inference applications, the size is very small. The application size is only like 2 megabytes, 3 megabytes. The runtime itself is 30 megabytes, 40 megabytes. We're talking about Wasm Edge here, but all the other runtimes are the same. If you compare that with, say, the non-portable Python PyTorch runtime, can you guess how large is a PyTorch-based Docker image? It's 4 gigabytes, right? It's 4,000 megabytes, so it's 100 times difference. So we're talking about 2 orders of magnitude difference in the lightweightness. And also the speed is much faster than Python. And also it is truly portable. At least we can make it truly portable, right? So how do we do that? There's a specification that is that grew up, I think, from Intel almost 3 years ago. It's called WASI neural network. It is now being adapted into component model and WASI preview too. But so when WASI-NN first came out, it was mostly to run smaller models on the edge. So for instance, PyTorch TensorFlow models that are on camera devices and things like that. You've heard about those stories today as well. So, but I think WASI-NN is now being adapted to run very large models, like large language models, and also stable diffusion and models like that. So the specific thing that we did, and we were hoping to standardize that as well, is to build WASI extensions to WASI-NN. So meaning the way WASI-NN works is like how every single WASI spec works, is that there's host functions being defined in the Wasm side, and then native functions on the host side, right? So there's so that provides opportunity to provide a different backend. So for instance, WASI itself, you can make it run on Linux, you can read it on Windows, you can have different libc implementations for that. But for the WASI-NN, we now have large language model backends for WASI-NN, so that all the inference, all the heavyweight compute actually take place as native applications that wrap around underneath the WASI runtime, right? So so you can still use CUDA, you can still use Mac Mental, so the net effect really is that developers can standardize on the WASI-NN interface. So you write application not to CUDA, not to Metal, not to the AMD ROMC, not to any of those GPU specifications, but you write application to WASI-NN. You compile to Wasm, and as long as then you deploy it to a machine that has WASI-NN large language model backend installed, it would automatically translate all your Wasm function calls into the CUDA function calls on that machine, or the Metal function calls on the MacBook. So that's how it works. So I think that is a rather elegant solution for the portability problem. So it's the same thing that you need to install different JVMs on different CPUs, but at the Java bytecode level, it's write once, run anywhere. So we would have a lot more demos later. That's in a workshop. But just to summarize, what do we get? So we have a project called Llama Edge. So it's a derivative of the Wasm Edge project, and we have numerous backend to it. So we have the Apple Metal backend to it. We have the the NVIDIA backend to it. We have the runs the ARM CPUs, runs the Intel CPUs. We have 4 Linux Foundation interns. Those are graduate students that's working with us at this moment to add new backend to it. So for instance, we wanted to run better on advanced CPUs on the new generation of Intel CPUs, which has SIMD and AVX enabled. So there's lots of hardware and low-level innovations that is going on that we can use WASI as an envelope to wrap around those interfaces, so that application developers only need to worry about compiling their application to WASI-NN and to Wasm. They do not need to worry about all the strange high-performance native code-based backends that runs those models underneath it, right? So I'll ask Vivian to come back and do the first demo. Use to write a cross-platform application for LLM inference.
Yes, so for the demo, I will first create an LM web service on my MacBook, and then I will run it on a NVIDIA device. So, okay. The source code for the LM web service is in the Llama Edge repo. It's all written in Rust. So the first step is that we need to compare Rust to the Wasm binary. I have already git cloned the repo, so we just and use cargo build target Wasm3 to Wasm release to compile the Rust source code. Compiling Rust will take some time. I believe that everyone have go through this.
So I want to emphasize this is compiling on the Mac and using all the standard Rust libraries. There's no compiling to the Mac GPU. There's no step like that. So it's all very standard. If you look at there's Wasm Edge WasmNN, which is our extension of Wasm, and we hope to make it to incorporate that into standard later. Cool. Yeah.
Okay, so next step, I will move this the compiled Wasm file to my root directory because I also downloaded the large language models here. So the Llama API server.wasm is the Wasm file we just compiled. The time here is a Singapore time because I just came from Singapore. Okay, so let's use next we will use Wasm Edge to run the Llama 2 model. Okay, this is the command line to run the large language models. You can use any large language models that in GUI format. So the API server is listening on localhost 8080. Let's open it in my browser. So let's ask a simple question. Write a hello world program in Rust.
The first interaction takes longer because it needs to load the whole 5 gigabytes model into the memory. But now it come back, so it runs entirely locally, So we could have turned off the Wi-Fi here, and this would still run, because the large language model has been downloaded into this machine, right? So it's so if you look at here, it's a local server, so it's a local host that it connects to the HTTP server, which also runs inside Wasm, and using the Wasm socket API, right? And then it connects to the local server that runs the large language model, and then the front end does that. Yeah.
So here is the program, but I don't think is it right?
Yeah.
Okay. So I'm not a Rust developer. Okay, so now we have compiled Wasm file on my MacBook. Next step, I will move the Llama API 0 Wasm file to the Jetson Orange device.
So by the way, that device sitting in our office in Taipei. So we have an engineering office in Taipei. The device is about this big. It's a Jetson Orin. It has it was designed to use in robotic applications. It has a small NVIDIA GPUs in it. So we put that in our office as a coding assistant. So we run a large, code llama model using Wasm Edge on that device, so that we hook up with all the IDEs in the office, right? So what she's doing is that we are copying this from Barcelona to Taipei, and then in a device that has entirely different CPU, entirely different GPU, and by the way, the performance there I have just seen on that chat interface is running on the GPU on the Mac, because if not on GPU, it wouldn't be that fast. It would speak very, very slowly, much slower than I speak now. But but it runs on the Mac CPU. Now she's copied that file into the Jetson device in Taipei, right? So now she's logging into the Jetson device.
Yeah, I have logged into the Jetson device, and we can see. So here is the Llama API server Wasm we just compiled. Okay, we can use exactly the same command line to start an API server for the Llama 27B models. So I just copy the command line I just used. Okay, so we can use the code to test the API server. Let's send an API request. This is the API request format to interact with the model. The question is write a hello world program in Python.
Yeah, so what's interesting here is that we started API server. The API server, we just show you, the API server has a web front end, but it also has an API backend, API endpoint that's compatible with OpenAI. Now it's already came back because, you can see the NVIDIA GPU is faster than the Mac GPU, so now it's, did it come back? Did it?
Yes.
Okay.
This is a simple hello world program in Python.
Okay.
From this demo, we can see that with Wasm we can develop and test LLM apps on our local machine and then deploy it on other machines without recompiling. So this is the first demo.
Okay, so yeah, that's so we have shown OpenAI compatible API server. That's a very, because it supports OpenAI style web services endpoints, you can actually connect a lot of tools with that. So we talked about you can do like LangChain with it, because you can use a lot of tools to hook up vector database to manipulate the prompt. There are lots of advanced stuff that people do with large language models these days. However, we don't want Python in there as well, because, one of the things that we learned is that, we have spent so much time in cloud native and we optimized the Go application and the Rust application. Now we are going all the way back to Python to deploy all those applications. And in fact, I personally don't want that. So we want to use Rust and Wasm to do the tooling that around the Wasm server as well, of the LLM as well. So this is one of the topics that Daniel mentioned earlier in his talk about the new Microsoft project, about using Wasm as a prompt, right? So basically they were adding Wasm to their application server to their large language model server, so that you can write a program in Rust to manipulate the prompt, to insert stuff into the prompt, and then to execute the program or the outcome that come out of the LLM to select, for instance, select a better answer. Or if you ask it to program in Python, it would run the Python program that's in your own application, right? So what we want to do is that I've seen a lot of demand, and we will do something that is similar. That's a lot of people have the same ideas. Is that we use Wasm to interface with the Wasm server we have just built, right? We have built a Wasm LLM server, but we want to use Wasm to manage the pipelines, while essentially provide a line chain alternative using Rust and Wasm. So that's the reason for that is really that's because those are extensions and plugins. We talk about those all the time. Wasm is one of the best use cases. Wasm is serverless functions and the plugins, and now we have large language models that definitely require those features. But now we are going back to use Python to do it. That's to me this is this is definitely going backwards. So we want to go forward and using Rust and Wasm to do that. So so the specific tool that we want to show is one of the other projects that's based on Wasm Edge. It's called Flows Network. What it does is that it's a serverless function. There's lots of things like that. It's a serverless function platform where you can just upload your Wasm and it would execute that for you. Well, one thing it does is that it now can act as your server. You don't have to start your own server. So hence, it's called serverless, right? So Vivian would come on again and talk about how we create a Wasm application for a Discord bot. And to connect that to the large language model service we have just built.
The second demo is to demonstrate that Wasm is the best runtime for LLM extensions. So Flows Network is a serverless platform powered by Wasm Edge. So let's do our second demo. So here is source code for building a Discord bot with open source LLMs. It's also written in Rust, so we will need to compile the Rust code to Wasm again. But instead of compiling on my own MacBook, the platform Flows Network will compile the Rust code for us. Okay, so let's go to Flows Network and click on Create Flow, and click on import the flow function from GitHub repo. Flows Network uses GitOps, so we will import the source code from GitHub repo, not compiling the source code in your own machine. The folder is Discord. And now we need to add some configurations for this LLM agent. Because it involves Discord, we will need a Discord bot token. The Discord bot token can be get from Discord developer portal. Click on New Application and name it Wasm. Click on bot, and then we will get the Discord token. And then copy and paste the Discord token here. Let's continue set up our Discord bot. We will turn on the presence intent, the server members intent, and the message content intent, and click on Save Changes. And then we will go to OAuth 2 to give some permissions for our Discord bot. And then an invitation URL will be generated automatically. We will copy this URL and open in the browser. And let's invite the Wasm 2024 bot to my own Discord server. So we can see that here is a bot called Wasm 2024. It's offline right now, but don't worry, it will be online quickly. So let's go back to a Flows network and continue setting up some configurations. The first is LLM endpoint. I have used ngrok to turn my local host 8080 to be an HTTPS link, so we can use this link. The API server is OpenAI compatible, so we will add Vivian at the end of the link. And the next is we will set some simple system prompts for the bot. Let's just say you are a helpful assistant. Okay, now let's build this function and click on deploy. So you can see the Rust code is building now. This is a building log for building a Rust program into Wasm. Oh, sorry. Again, it will take some time because compiling Rust is. Oh, okay. Oh, it's online now, so we can go back to our Discord server, and you can see that the Wasm 24 bot is online now. Now we can. Oh, sorry. One more thing. I need to. I will use Wasm to start the API server for our Discord bot. So this is the same command line in the first demo. So I think now we can talk to the bot. So in the terminal, we can see the conversation history. I just sent a hi, and I think now the bot has a response to me. So I think this demo is done. I'm not going to ask some complex questions since our time is all right. Okay, so.
Maybe you can put the link up there so that if anyone's interested, you can add this bot to your own GitHub Discord server. Yeah.
Yeah. So this is our LLM agent demo, and you can also use. We also developed some LLM agent based on ChatGPT. That time you can go to Flows network start page to check them. So besides, Michael and I have discussed and demonstrated Wasm continually want to improve the LLM app development experience. So in the future, we will add more LLM-related backends for the Wasm plugin. It will have MLX, it's for the Apple chips, and we will have Intel extension for transformers, it's for Intel chips, and we will have more models like OpenAI's Whisper, it converts text to voice, and we will also have Burn. It's similar to Llama.cpp, and we will also add support for embedding models, which is important to develop RAG applications. And we will also figure out some ways to do Wasm container management on GPU. So this is our plan. And this is a resource that we use in this talk, including the Wasm proposal, the Wasm Wasm crate, and the Llama Edge, and its source code, and also the Wasm serverless platform flows network. So in the afternoon, Michael will have a workshop on building LLM inference on the edge cloud, which will introduce more LLM features in Wasm Edge. If you are interested in, you are welcome.
All right, thank you, Vivian. Yeah, that's I think we are right on time. So we won't hold up for lunch. So we hope to see you after lunch. That's in your workshop.